Okay, good morning, everyone. So this chapter is about functions, right? Chapter 3 is about functions. And basically we've just been introducing basic basic concepts, right? The idea of a domain, the idea of the range, the image, right? We've done section 2 was on graphs. Section 3 was on things related to what's called optimization. Optimization, so like finding the maximum value, finding the minimum value, and then sort of thrown into that was this idea of average rate of change, which maybe doesn't look so, maybe the relation to optimization isn't so clear, but once you get to calculus, you'll find that average rate of change turns into something called instantaneous rate of change. Instantaneous rate of change. So once you combine it with the notion of limit, it turns into this thing called instantaneous rate of change, which is in calculus has another name, the derivative. Okay, the derivative. Okay. Some of you are nodding, and some of you may have seen this before. So that's kind of one of the major ideas of calculus. Okay, so we're just talking about functions today. We're going to introduce a few more ideas. The first set is called translations and reflections. Okay, so you can think of this as maybe as a sort of combination of domain, the concepts of domain and range, plus arithmetic. Okay, or you can think of it as getting new functions out of old functions. Okay, so that's sort of what we're doing in the next two sections. Creating new functions, creating new functions from old. Or recognizing, or maybe even better, recognizing functions as variations of simpler ones. Recognizing complex functions as variations of simpler ones. Okay, that's I think probably the best way to think about these next two sections. Okay, so let's start off with that. So it's pretty simple idea. So you have some function. So f of x. Okay, so you have some function f of x. Maybe it looks like this. Say. Okay, maybe this is this graph. Okay, and then you say, okay, I'd like to, think about variations of this function. So I'm going to create a new function. I have a constant, so c is some constant, a positive constant. Okay, and then we're just going to use, create a new function by taking our old function and adding that constant to it. Okay. Okay, so take 10 seconds and draw what the graph of g would look like on this same graph. Okay, so what would the graph of g look like here? If this is the graph of f, right, so this is y equals f of x, what does y equals g of x look like here? Okay, turn to a partner. Talk with them just a little bit. Okay, this is maybe pretty straightforward. What is it going to look like? What's it going to look like? Yes?
Just like shifted upward.
It's shifted upward by c. So whatever c is, let's say that c is, C is this number here. Okay. Then you take, all you're going to do is take every, take every point and shift it up by C, right? If this point is x comma f of x, well, x comma g is going to be f comma x comma f of x plus c. So it just gets shifted up by if you shift it up by c, you get f of x plus c, but that's g, right? So the graph is going to look like this. Okay. Right. So this is what's called a translation. This is called a translation. Right. And if I said minus c, then it would just shift down by c, right? And that would also be a translation. Okay. What if I have something like this? G of x equals f of x plus c. Again, take a few seconds and draw what that would look like. Okay, talk to a neighbor, please. Okay, this one is maybe a little bit trickier. Does anybody want to tell me what they think?
Is it shifted to the left by C?
Shifted to the left by C. So you take this guy and then shift it over by that amount. So everything would move over by this much. So you get something like this. Oops. It's not right. Sorry. Come down. Sorry. Like this, I think. Right. Okay. Anybody else? Anybody else? That's right. That's right. Just to see if anybody would fall into it. But that's right. The way the way I think of it is that right. So you take some point x, right? So you take some point x here, right? But the y value is going to be from over here, from x plus c. Right? So let me. So I have some function y equals f of x here. I have this other function f of x plus c, right? So to figure out the graph of this function g, to figure out this graph of the function g, I say, okay, well at x I'm going to have the value f of x plus c. So here's x plus c. So my y value is actually going to be from over here, right? My y value is going to be from over here because this is the graph of f here. This is the graph of f, and at x I need to take the y value from x plus c. So this is going to be my y value. Okay. So everything gets shifted over. Everything gets shifted over to the left by c. Okay, right, makes sense? Right, another way I like to think about it is, I think of this in terms of time, right? So this g function is basically doing everything that the f function does, but a little bit ahead in time, right? So if this c were 1 and t were in seconds, then whatever f does, g is going to do it 1 second earlier, right? Because g does things at x plus 1, right? So at time 0, when time is 0, it's doing what f is doing at time 1, right? and so on and so forth. So I think that's kind of a useful way of thinking of things in terms of this is a shift in time. So notice what's going on here. These guys here are a shift in the range, right? So the y values change, right? The output is what's being added to, and here the input is what's being added to, right? So you're affecting the input. Here you're affecting the output. Okay, so here you're sliding it to the left, right? Because you're sliding, you're affecting the x-axis basically, and here you're sliding it up because you're affecting the output. Okay, so this affects the output, and this affects the input, which of course affects the output. Okay, right. Okay. So, and again, if I have f of x minus c and c is positive, then I'm going to shift in the opposite direction, right? It's going to be slower, right? It'll be x minus some. It'll have a delay of c rather than an advance of c. Okay. So so this is also called a translation. Where you take the whole graph and slide it around. Okay. So you can combine these things, right? You could have, say, like f of x plus c, f of x plus c plus c, say, and that would be, you would shift it backwards and then shift it up, right? And that would also be called a translation. Okay. So that's a particular class of transformation called a translation. Okay. So these are translations. Okay. And then there's another class of things called reflections. Where you take the function and you, let's do this, so you multiply it by -1. Okay. So right, you have your function, y equals f of x, and then you create this new function, y equals negative f of x. Right. What's going to happen? Somebody tell me? If you're on this graph, then all your coordinates are x, f of x, right? If you're on this guy's graph, all your coordinates are x, negative f of x, right? So they're all going to have the negative y coordinates. Right? So it's going to be a flip, right? This point will turn into this point, right? And so on and so forth. You get this. You get this sort of thing. What's called a reflection. Okay. And what about if I have g of x as f of negative x? What would that be? So?
If I did the other way across the y-axis.
Yes. So you take all the x values and then reverse them, right? So that is you would reflect it across the y-axis, right? So this thing here, x, right? That would happen. That value would occur at negative x, right? So that value would occur at negative x. And so the graph would look like this, right? So you get a reflection this way. Okay. Again, notice that the first one affects the output. The second one affects the input, right? You're taking the output and you're reflecting it, and here you're taking your input and then reflecting it. In other words, you're reversing time. Right? You're reversing, in terms of time, the time analogy, you're reversing your time. So, right, anything that happens at this time actually is going to happen at the reverse time. Right? And so the image is going to be backwards. Everybody, is this okay for people? Anybody have questions? Okay. why do we do this? Like I said, this is we're gonna use this to sort of recognize more complicated functions as versions of simpler functions. Okay, so we'll say, so here's an example. We have this function f of x. No, I'm going to say g of x is x squared plus 3x plus 2. Okay. If we do our completing the squares trick on this, what are we going to get? Well, this thing would turn into x plus 3 over 2 quantity squared minus 9/4, right? Right? Right. And then we have this plus 2. Right, so this turns into x plus 3 halves quantity squared minus a 4. Okay, but you can recognize that, right? This is a double translation of the x squared function, right? So if we think about f of x, if we take the function f being just the squaring function, well, you see that g is just a translation of it, right? Right. All it is you take f of x plus 3 halves, and you subtract off a 4. Right? So you know what that graph is going to look like, right? You take the f of x equals x squared function, and you're going to shift it to the left, right? Because time has sped up by 3/4, right? So you shift it to the left by 3 halves, and then you shift it down. You shift it down by 1/4, right? So it's going to be shifted left and then down. Right? So you get this increment. Right? Okay. So this is a simple example of so we have this thing that looks kind of complicated, and it turns out that it's just a translation of something simple. Okay. So it allows you to understand this thing better, and you see that in fact every quadratic is going to be just a translation of x squared. Right? We could have done this with whatever numbers, and we would have ended up with some sort of translation. Okay. Here's an exercise for you to try. So you have a function f of x equals negative x cubed plus 3x squared minus 3x plus 1. Excuse me. So negative x cubed plus 3x squared minus 3x plus 1. And then you have a bunch of other guys. So the first one is negative x cubed plus 3x squared minus 3x minus 1. The second one is x cubed plus 3x squared plus 3x plus 1. The next one is x cubed minus 3x squared plus 3x minus 1. And the last one is negative x cubed minus 3x squared minus 3x minus 1. Okay. And so the game is express these functions in terms of f. Okay. They're all some like some sort of reflection or translation, or reflection plus a translation, or whatever. Some sort of combination of these basic operations. You take that, you do it to this, and you get this one. Okay. So we want to recognize this as f of something, f of what plus what, or so what is this function in terms of f and the translations and reflections. So see if you take 1 or 2 minutes and see if you can do that. Okay, turn to somebody nearby and talk with them, please. Okay, anybody want to tell me about the first one? First one? I used to bring in a gigantic 20-sided die and choose people at random based on the die. These days, my children have taken the die from me, so I'll have to steal it from them, I guess.
Would it be
Yes.
f of x minus 2?
Yes, that's right. So this is, right, you see that, what's the difference between this one and this one? Well, it's just been shifted down by 2, right? So this is f of x minus 2. Yeah. The children are using the die to decide how much they need to practice piano. So they're like, da, 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 da. Oh, I got a 1. I only have to practice my pieces 1 time, right? But if it ends up on 20, well, they actually have a rule that if it's above 11, they subtract 10. So it mostly practice 11 times. But yeah. I don't know if this will amuse you, but for some days, I noticed that my daughter was only practicing things 1 time, and I said, "What happened?" Actually, at that point, she was increasing the numbers by 1 a day, like 1 the first day, 2 the second day, 3 the third day. And she said, "Dad," she's 7 years old. She said, "Dad, I had to practice 17 times yesterday," or something like that. And she said, "Now I'm squaring numbers." And I'm like, "But the square of 1 is 1." So like she was starting from 1 and squaring, right? So every day it just turns into 1, right? So I was like, "But the square of 1 is 1," and both she and her older brother were like, so. I don't know if that's amusing, but anyway, B. Can anybody, what's B? Anybody get B? Yes, Zoe.
Well, I'm not sure where that would be f of negative x.
F of negative x, yeah, right? Because you notice that all of the odd terms have changed sign, right? The odd terms change sign, and so that if you have f of negative x, that's putting the negative x into here, the x, that would give you negative x cubed, negative x cubed, which is just x cubed. The square guy is not going to be affected by that, right? Because when you take the square of a negative number, nothing happens. When you take, this thing isn't affected, but the odd terms would all change sign. Good. Okay. What's the next one? What about the next one? Yes, Amy. Negative f of x, yeah. Right, so you notice that everything has changed sign, so it's got a negative sign in front of it. What about the last one? Anybody? Does it look, do you need a hint? The hint is, look at one of the earlier ones. Do you see any earlier one that looks vaguely similar? Yes, Amy? Yes. So this is f of negative x, and if we put another negative sign on it, right, afterwards, right, we're going to get we're going to get this. Okay. Okay. Maybe that's all I want to say about this section. Here's one more example I wanted to do, but I don't think I can explain it properly. So let me think about it a little bit more, and I'll do it next time. So instead, let's go on to section 3.5. Neither of these two sections has that much material in it. So this is again sort of creating new functions from old, but where what we were doing before was just taking one function and messing with it. Now we're going to combine functions. So we've got like pairs of functions from old functions. So this is arithmetic. Okay. So this is kind of what you would expect to do. We define a way of adding functions, right? We say if you have two functions, so given two functions, f and g, we define the new functions, f plus g by f plus g takes in a value, and it gives you back the sum of the values of f and g. Okay, so this is kind of what you would expect, right? Right. So we create this new function called f plus g. What does it do? It gives you back f of x plus g of x. Okay, you should not. This is not, not the most impressive thing. Okay, so if I have some function f of x equals x and g of x equals say x cubed, then the new function, what is it going to do? It will give me back f of x plus g of x. In other words, x plus x cubed. Okay, so nothing impressive. Okay, so that's all I'm saying here. We can create a new function by doing the obvious thing. Okay. Similarly, you define a product function, you define a quotient function, right, and so on and so forth. Okay, so this is really notation, right? This is more of notation than anything else. It's not really a new idea. It's a notation. The only thing you have to worry about is that this guy, the domain might be different because you have to watch out where g is 0, right? So there's a little warning that domain excludes where g equals 0. Yeah, I guess you have to be a little bit cautious about the domain. So where would the domain of f plus g be? If you have a function f, it has a domain. You have a function g, it has its own domain. Where would the domain of this sum function be? Where the two domains overlap, right? So the domain of f plus g is going to be the domain of f intersect the domain of g, right? The points that are in the intersection, right? So like if this were the domain and this were the domain, then both these functions have to be valid. So you need to line the place where both of them are defined, right? So you look at the intersection. And similarly for the product, but I mean, most of the time you don't need to worry about that. I guess the only one that, like I said, the only one that's a little bit important is this one. Okay. So that is kind of a simplistic way of combining functions. There's a much more sophisticated way called composition. Okay, so this is not arithmetic. This is where you take the output of one function and you feed it into another function. Okay, so like, right? You have two functions. You have two functions f and g, and so right. Remember, we can think of this as a map from the real line to the real line. Right, so it takes in a real number, spits out a real number, right? And similarly for g, right? G takes in some real number and then spits out a real number. Right? Okay, so we define the composition let's say G composed with F by G composed with F of X equals G of F of X. So this is read G composed with F. And if I had written it the other way, it would have been F composed with G. If I had written F circle G. So pictorially, what's going on is that for G composed with F, what would happen is that you start off with your F, so X gets mapped to F of X, and then you would take that output and map it through G. Right? Take that output and map it through G and get something G of F of X. Okay. So you take the output of one function, use that as the input of the next function, and then do it again. Okay. So like if I have f of x equals x squared, say, and g of x equals x plus 1, right? Then g of f of x would be obtained by taking the output of f and feeding that into this guy. Right, so you take the output of this guy and you put it in as the input of this guy. Okay. It actually probably makes sense to use a different variable for g. I'm going to write it like this. Okay. So you take the output of you guys, maybe I'll use z because people sometimes think of y as, I'm going to use z as my dummy variable. Okay. So you take this output, you feed that in as g's input, and you get something out. Okay. So what do we get out here? Anybody want to tell me? This is going to be g of f of x. Well, what is that? Write something down. Take 5 seconds, write something down. Okay, talk to a neighbor. Okay, what do we get? G of f of x is x squared, right? So we take the x squared and we use that as our input of g, right? So our z is going to be x squared. right? So what's the output going to be? Z plus 1, right? X squared plus 1. Okay. What if we had done it in the opposite direction? f of g of, I'll call it z, because, right, we need to take f of g of z. Yes, sir.
Would be z plus 1 squared.
Yes, z plus 1 quantity squared. Right? So we get f of g of z, right? G of z is z plus 1. Right? So that'd be f of z plus 1. F takes something and then returns the square of that. So we're going to take whatever we're given and return the square of that. Okay. Okay. Notice that the composition is different, right? The order is important. If you change the order of the composition, the function changes, right? G composed with f is the function that takes your input, squares it, and adds 1, right? This guy, the opposite one, is you take your input, add 1 to it, and then square it, right? That's very different. Okay. I should say that most of the time when people are introducing composition, they write it like this. So they use the same variable. Okay. It actually makes more sense to use a different variable because you think of f being something that gives you return some value, and then g takes that value and then gives you something back. But often people will write it like this, right? And so you would say g of f of x is going to be g of x plus 1. I'm sorry, g of x squared, right? And then you see it's kind of awkward because then you say, then I'm going to let my x be x squared, right? I'm going to let my x be x squared, and that may be kind of confusing. But in any case, you let your x be x squared, and so you get x squared plus 1, right? And going in the opposite direction, f of g of x, right? G of x would be x plus 1. You say, okay, my x is going to be x plus, my input is going to be x plus 1, and so I get that thing squared. Okay, so anyway. Okay. What is the domain of G composed with F? This is kind of a semi-interesting question. No, it's not that interesting. So, it's something that you do have to look at. What's the domain of G composed with F? Right? If F has some domain and G has some domain, what's the domain of G composed with F? Okay. The answer is it's all x in the domain of F for which f of x is in the domain of G. All x in the domain of F such that f of x is in the domain of G. That's reasonable, I hope, because you might be tempted to say, well, isn't it just going to be the whole domain of F? But there might be some elements here that get mapped by F to a point that G can't handle, right? to a point that's not in G's domain, right? G's domain is up here, right? Maybe f takes these guys and maps them all outside of G's domain. Well, then G composed with f doesn't make any sense, right? Has no meaning there, right? So you can only take those points here, those special points here that f maps into G's domain, right? So only the points in f's domain that get mapped into G's domain. So for example, if I have f of x equals the square root of x plus 2 and g of x equals negative x. Okay, and I'm looking at, say, f composed with g. Right? So first I'm taking the g function, and then I'm taking the f function. Okay. Actually, let me get rid of this plus 2 for now, just to make it more straightforward. What would the domain be? What's the domain of this composition? Talk with a neighbor for half a minute.
So, this one doesn't look like right? Yeah.
Okay, Zoe, what were you going to say?
I was just thinking maybe just positive numbers.
Positive numbers. Let's see. So if we start off with a positive number 1, say, can we get f of g of 1? Well, that's going to be f of g is negative, so we get f of negative 1, right? But f is a square root function, so we get the square root of negative 1. So no. Anybody else? Yeah, Vivi. Negative numbers, yeah. Negative numbers will do it. So right, the way you want to think is like this. F is a square root function, right? What's the domain of f? The domain of f is the non-negative numbers, right? Here's the domain of f, from here upwards, right? And remember, we want the guys in G who get mapped into the domain of f. G is the multiplied by negative 1 function, right? So what's going to get mapped into the domain of f? All the non-positive numbers, right? G's domain is actually the whole line. Right? G's domain is the whole line, but some of those don't work, right? Only the ones that start at 0 and go down from there get mapped into f's domain, right? So you see that's how that works. Okay. Slightly trickier one. What if f were f of x plus 2? Sorry. What if f were the square root of x plus 2? But same G. G of x is multiplied by negative 1. F of x is take the square root of x plus 2. 2. What's the domain of the composition? What's the domain of the composition?
Is it negative infinity to positive 2?
Negative infinity to positive 2. I think that's right. So let's think. What's the domain of f? The domain of f is going to be from negative 2 upwards, right? Right. So from here upwards like that. Right? And then you say, okay, well, what is going to get mapped into that by g? Well, everything from positive 2 downwards is going to get flipped by g into there. So yeah, that's right. Right? So it's going to be everything from 2 inclusive up to positive infinity. Sorry, what am I saying? It's from negative infinity up to 2 inclusive. Okay. We'll start somewhere around here next time. Yeah, we haven't finished this section, so we'll come back.